Hello and welcome to another LeetCode video. Today we're going to be doing problem number 875, Koko eating bananas, and it's a popular interview question right now. So I wanted to go over it. And so pretty much the question is, there are piles of bananas and the Koko has 8 hours, or not 8 hours, 8 hours to eat all the bananas in the pile. And Koko decides her banana eating speed of K. And so for every pile, every hour, she chooses a pile of bananas and eats K bananas from that pile. And if that pile has less than K bananas, she eats all of them and will not eat any more bananas during this hour. So she wants to finish eating before the guards return, but she likes eating slowly. So we're trying to minimize K such that she can eat all the bananas within 8 hours. So let's take a look at these examples, and hopefully we can better understand the question. So we have 3, 6, 7, 11, and we have hours equals 8. And we want to, remember, we want to minimize K. So they're saying the output is 4. So let's take a look at what that would look like. So you can eat 4 bananas an hour. So during hour 1, you can just eat these 3 bananas. And then we have to figure out how long does it take to eat each pile, because it doesn't really matter in which order, we just have to figure out how long. So if there's 6 bananas, and she eats 4, then there's 2 bananas remaining in 1 hour, and then she comes back and eats the rest of them. So this is 1 hour, 2 hour, 3 hours total. So we have 3 hours, then 7 bananas. It's pretty much, we have to just figure out, like, if you can eat 4 at a time, how long does it take to eat the bananas? It's pretty straightforward. So 7 would take 2 hours, and then yeah, if there's less than 4, then she would just eat whatever's left, and that would take up the whole hour. So this would be plus 2. And then 11 would be 3, because it would be 4, 4, and then you'd have 3 left over, so it'd be 3. And then this would be 2 hours, 2 hours, 1 hour. So you have 1 hour, 2 hours, 2 hours, and 4 hours, which is 12 hours. Or no, I did something wrong here. You have 3, right? So 1, 2, 2, 3, and that would be 8. Okay. And so this is 8 hours. And so we are just coming at, like if we know that our hours to eat the bananas is exactly 8, most likely we can't choose a better solution, but let's see if we can, right? So let's try 3 bananas per hour, and what would happen? So if we eat 3 bananas per hour, then this would take 1 hour, this would take 2 hours, this would take 3 hours, and this would take 4 hours, which is clearly too much, right? Because for like 11, you can eat 3 during 1 hour, so you get 8. You eat another 3, you get 5. Eat another 3, you get 2. Eat another 3, you get 0, and so on. And so if you do have like some remainder that's less than 3, it still takes you an hour to eat that. Okay, so that's that first example, is why it's 4, and you can't eat any slower than 4. Let's look at the second example. Hopefully, I'm gonna draw it a little bit better and try to show how this works one more time. Okay, and so they're saying you have 5 hours, and the output is 30. So they're saying, yeah, so this one's kind of obvious, right? So there's 5 piles. So maybe this isn't like the best example. There's 5 piles in 5 hours, which means you have to eat 1 pile in 1 hour. And so that means that the minimum, like K, would have to be the biggest element in this list, because you have to eat each pile in 1 hour. And so the biggest element in this list would be 30. So that's how they came up with that. Let's go to the next one. You get a better example. So 30, 11, 23. Okay. Now we have h equals 6. Okay. And so they're saying the output is 23. And so what would happen if it was 23? Okay, well, this pile would go down to 7 in 1 hour, and then would go down to 0. This pile would go down to 0 in 1 hour. This pile would go down to 0 in 1 hour. This pile would go down to 0 in 1 hour. And this should actually be a 20, not a 26. This probably should go down to 0. And once again, intuitively, you can kind of figure this out, because you only have 6 hours and you have 5 piles, which means 1 pile is going to be eaten in like 2 steps. And so in that case, the answer would be the second biggest element in the list, because you have to eat every other pile in 1 step. And so here you can see this 5 steps here, and then 1 step here, and that would be K equals 6. The problem is this isn't always the case. Like if your list gets really big and your hours gets really big as well, then you can't just be like, okay, well, how do I figure out like how many iterations do I do this in? And like with this kind of thing where you take the max and you take the second max and things like that. So we have to try to think of a better solution. Because if we were doing that, yeah, and our array it can be up to, like 10 to the fourth element, so we can't take like the 1000th max or something, Okay. So what we need is we need a better solution. And so let's just say we had some numbers like 5, 4, 8, 20, 30 maybe, whatever. And then our number of hours, let's say is 10. So what would be the brute force solution? So for the brute force, it's pretty straightforward, but let's kind of get an intuitive brute force solution, and then we can figure out how to optimize it. So first of all, we got to realize that actually to figure out like if our k is possible to do, it doesn't actually take a lot of time. Like we pick a random k like 1, right? How long does it take for us to figure out if for 1 this is a valid solution? Well, we'd have to go to every element. We'd have to divide it by k, and then we'd have to see is there a remainder, and if there's a remainder, we'd have to add another one, right? So our steps would be like, write this down. So go to element, divide by k, check for remainder, right? So that would be our steps here, and that wouldn't take very long because. So I guess this is like all 3 steps, but so 1, 2, 3. So like here, we would divide by k, so we would get 5. Divide by k, we get 4, and so on. And clearly we can realize for this, k would be too small. Okay, well, what if we just try 2? So for 2, let's delete this. So for 2, let's try our steps, right? So we go to element, we divide by k, so we get 2 here. Now we do have a remainder. We have a 1 remainder, so we need to add 1 here. So let's add a 1. We get a 2 here, no remainder. We get a 4 here, no remainder. 10 here, no remainder. 15. Okay, once again, too big. So let's keep going. Okay. Let's try 3. So we get a 1. We do have a remainder. We have a remainder too, so we need to add another 1. We have a 1. We do have a remainder. We have 2 with a remainder. This needs to be 1, right? Every time we have a remainder, we just add 1 to the hours because Koko will just eat the remainder in 1 hour. And so here, this would be 6. We do have a remainder. This would be 10. So let's add this up. So this is 20 hours. Still too big, right? So we need to keep going. Okay, so let's try 4. Okay, so it's going to be 1. We do have a remainder, so plus 1. 1, no remainder. 2, no remainder. 5, no remainder. 7 with a remainder. And so this is going to be 2, 8. Still too big. Okay, it doesn't work. All right. So like I said, we're just really trying to get the intuition for how we're doing this problem. So we're going to try 5 next. So this 1, 1, 1 plus a remainder, 4, 6. 2, it's still too big, right? Because this is like 14. Okay, so let's try 6. Okay, 1, 1, 1 plus 1, 3 plus 1, and 5. So what do we have here? So we have 4, 2. Still a little too big, right? That's going to be like 12 or 13 or something. Okay, let's try 7. 1, 1, 1 plus 1. 2 plus 1, 4 plus 1, so we have 5, 3, 2, still a little too big. Okay, sorry, it's kind of repetitive, but I hope you're kind of getting like what you're doing here. So 1, 1, 1, 2 plus 1, then we have 3 plus 1. Okay, so this is 3, this is 6, and this is 10 exactly, right? So I think that's the solution here. And so now that if we hit 10 exactly, like I said, and especially if we're going from the smallest, like if we're starting at 1, so that could be that's a brute force. So you start at 1, you keep going until you get a solution, right? You keep going until you hit a solution that's under hours, and then the first number you are, so we can write that down as well. So start at 1 and keep going till hours is good, right? So if we can finish in H or less hours, then we have a solution because we started at 1, and so we're guaranteed like the first thing we run into is going to be solution. But what's going to be the time complexity of that? Well, let's think about that, right? So we're going to start at 1 and we're going to go to hours. So actually, no, we're not going to go to, yeah, we're not going to go to hours. Sorry, we're going to go to, technically, this can go to the biggest element in the array, right? Like for our first example here, where we actually need the biggest element in the array. Well, if the biggest element is like 10 to the 4th or something, well, let's actually take a look at what the biggest element in the array could be. So, so piles I could be 10 to the 9th. And so worst case scenario, we can have something like 10 to the 9th, right? So it would be 10 to the 9th times, and then the length of the array, right? We have to check the entire array every time. So that's 10 to the 4th, and this is like a quadratic equation, and this is going to fail. So what we really need to do is we need to try to like, I mean, I think even at 10 to the 9th solution will fail. So we need to really figure out a way on how to like simplify this 10 to the 9th. And usually the way to do this, yeah, so we're going to need to simplify this into either a of n or better. Or sorry, we're going to need to simplify it to log n, all right? So that could work. So if we have n log n, that could work. Like if we have 10 to the 4th and then log of this or something, or log of one of these, that could work. And so how would we do this? Well, it's actually even pretty intuitive. So instead of brute forcing every single number, what we could do is we can just binary search, and we can, and so what's going to be like our max k? So our max k, like what's our left and our right? Well, our left is going to be like 1 banana, right? Because if you eat 0, then you're eating nothing. And then our right is actually going to be the max of the list of this array, right? Because like worst case scenario, you would want to eat like the biggest one, and there's no point in eating the biggest one, or there's no point in anything any more than that, because you can still eat every pile in one hour, and that's the best case you can do. So the max is actually the max of this list. That's going to be the rate, and so we can just simply try every single, or not every single, but we can just go from these two, right? And we can just find the smallest k possible using a binary search. Like we can just keep trying numbers of k and say, okay, is this under hours, is this under hours, is this under hours? And we keep trying to minimize that. And the smallest number is going to be our result. So once you can see with the brute force, like all we're literally doing is just iterating through each pile and counting up, did we do better? Like, did we get under 10 hours? Then you can kind of realize the way to speed that part up would be a binary search. And then that would make the solution of a log of 10 to the 9th times 10 to the 4th complexity. And that would pass. Because log of 10 to the 9th is probably like, I don't know, 50 or something. So then we have almost a linear solution. Not quite, but close. And so that's what we're going to be doing. We're going to be doing a binary search through the k values, and then we're just going to run through the array and count up. And there's no way to, like, we have to run through the array every time. We can't, I don't think there's like a faster way of doing it. At least not as far as I know. So you have to run through an array and figure out like how many hours would it take with my given k. And if my k is under hours, then I would, sorry, not if my k is under hours. If my hour, like if my hours it took, match the criteria of hours, then I would try to minimize k. And so the way our binary search is actually going to look like is, so this is like the way I like to do binary search. So we're going to go from 1 to like the max element here. And then we're just going to say if hours are met, then we minimize k, meaning we're going to have some variable to keep track of like what's the smallest possible k we have. And if this k is less than our smallest variable, then we're just going to replace that. And then we are also, remember, so if the hours are met, we're going to minimize k. That means go left in the binary search. And then if hours are too big, right? So let's say I guess not too big, if hours are not met, right? So if hours are met, then we can try to minimize k because we know like if for k equals 9 we have a solution, then we need to just try k is 8 and less. We don't need to go like to the right, right? But if hours are not met, if it's too slow, then we will go right and make k bigger. And so those are kind of our two cases, right? And so if we have like let's say for k equals 9, our hours are met, then we need to try 8 and less, right? So we need to try everything less than or equal to 8. But then if we try 9 and it's too slow, then we need to try 10 and more. Okay, and that's pretty much going to be it. So let's actually code it up. So remember, we're going to have a binary search here. And so our biggest value is going to be the max element in piles. You could honestly, if you wanted to, so taking the max element in piles will save us a little bit of time, right? Because what you could do is just like hard code in 10 to the 9th. Like you could just say like, okay, well the biggest value here could be 10 to the 9th, so I'm just gonna make right 10 to the 9th. But and it should be the same time complexity, because like if log 10 to the 9th is like 100 or 50 or whatever, it's gonna be like 50 times n time. Where if you just take the max element, it's gonna be the max element. It's gonna be like, you know, let's say your max element is 20, log 20 is like 3 or 4, so that'll be like 3n. But yeah, like it'll be the same time complexity technically. But we're just gonna take the max element. So we're gonna say left equals, remember, like the least we can possibly eat is 1, right? We can't eat 0, otherwise we never get anywhere. So left equals 0, right equals max piles. Okay. And now we also need the actual result that we have. So let's just say result. Remember, we're trying to minimize it, so let's just make it negative infinity. And I do think there is always a solution here. I'm not exactly sure, but I'm pretty sure. Like there is always going to be let's see, piles length, hours. Yeah, so hours is always greater than or equal to piles length, which means if you just make your k the biggest element, then you're always going to have a solution. Okay, so we're going to have a result of, well, actually, sorry, we're trying to minimize k, so we're going to start it with infinity. Yeah, we can actually even call it k instead of result. So we're trying to minimize it, so if we're trying to minimize something, we want to start it with infinity. Okay, then we're going to have our binary search. And then, so pivot equals. Okay, so now we actually need to go through, remember we need to go through our array for our given k, which is the pivot. So we can actually make it a little better. So we can make this the result, and we can make this like the k that we're trying currently. So when we get a k, we need to go through this list, and we need to figure out like how many hours does it take to eat the pile. And like I said, like if, let's say your k is 8 here, what you need to do is you need to divide the number. You need to do an integer divide by like 8, so you get 3. But then you also need to check, is there a remainder? And if there is a remainder, that's going to take 1 more hour, right? Because like you have 30, in 3 hours you would eat 24, and then you have 6 left, which would take another hour, right? So it says when the pile has less than k bananas, she eats all of them instead. So that would still take an hour, and she's not going to eat anymore. Okay. So we need to loop through the numbers and do that, and we also need to have like a total that we keep track of. So let's just say total equals 0 here, and then for let's just call it banana or whatever, stack and piles, stack of bananas. Okay, so we need to do total plus equals stack over k, and then we also need to check for the remainder. So if stack mod k, meaning if there is a remainder, then we need to add another one. So okay, yeah, so that's that for iterating through the array. Now we just simply check the total and the hours. So if total, is this total? Yeah, it's total. Yeah, so total is the amount of time. So it's probably not the best name. Let's just make it time. Yeah. Okay. So if time is less than or equal to hours, that means we hit a requirement. So now we check for the result. So result equals min of result and rk. And then remember, if we did hit like a valid k, then we need to check to the left, because if the k that we currently have works, then we only need to check to the left, because anything to the right of this k would just be a worse solution. So if we need to go to the left, that means it's going to be what? Okay. And then otherwise, our k was too small, so we need to increase it. So it's going to be okay. And we just return result here. Let's see if we made any mistakes. Right, so this should be h. Can't spell. Is this max? No, this is not the max. This is the minimum. We're trying to minimize. Right? Yeah, we're trying to minimize the result. Okay. Okay. Anyway, so that's going to be solution there. And let's actually do the space and time here. So time, so remember, for the k that we're getting, we are doing a logarithmic approach there. And so that's going to be log of, and let's just say this is like the max number of piles. So whatever the max number in the piles is, it's going to be the log of that, because we are trying 1 to that number. Okay, and then also we're doing that how many times? Well, it's going to be n times, but what is actually n here? So for n, we need to go through our stack every time. And so that's going to be like, so this could go of, and then this number is actually going to be the length of piles. So let's just say length piles times the log of the max number in piles. So that's going to be the time. For space, we didn't actually store anything, I believe. Yeah, right? Like we have a left and a right, but we didn't actually store any other elements. That's going to be big O1. Okay, so that's actually all for this problem, I think. And if you did like this problem, then please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching. Bye.